Good morning. I'll start with returning the homework. Nisha, Ronnie song. Thank you. Anirudh, Vitali. No, this one. Daniel Person. Kim Ma. Hannah Femi. Benjamin D.
Yep.
Jimena. Wait. Cody W. Basel Hamien. Alex L. High. Morgan K. Sunanta Sentinel. Jason Yang.
Here.
Victor C. Thank you. Lee Paul.
Here.
Keith McGinnis. Jeremiah Pesca.
Here.
Una Maravi. Kobe Davis. Juan Sian. Robert Longacre. Andrew Wyatt. Daniel Josky. Rodion P. Frank San. William Newcomb. Belen. Cameron Nakasone. Andy Beruca. Andy. James Kramer.
Yep.
Jeffrey Lerta. Andrew Gonzalez. Carson. Jacob Collins.
Here.
Jacob Collins. Tim Coutinho. Ray Emory.
Here.
Evan Johnson.
Here.
Daniel Durica.
Yep.
David Gilmore.
Here.
Thank you. Sam Bernada. Sam? All right. Yes. I don't see. Yes, thank you.
I think you had your name, but I might not have you.
This one?
Yes.
So, how are you? I'm sorry?
You have homework 4? We turned in 2 homeworks last week.
And this I return is 5.
Yeah.
And he's graded.
Is homework 4 not for you?
I don't know. I found this in the graded folder, so I don't know. This is what I have. Sorry. We have a rule that the grader cannot work more than 20 hours a week, and so I cannot push them to grade it faster than they are doing. This is graded, right? Fantastic.
You already uploaded.
I uploaded,
Yeah, all the grades are uploaded.
and so they didn't return it yet to me. Sorry. Hopefully it will be here on Wednesday if we do it.
So,
All right. So we have, yes.
is the midterm going to be from the very beginning of this one?
So other people ask me this. So in the first half, we learn what is a function and what is an injective function, right? In the second half, we learn that the set is countable if there is an injective function from the set to the natural number. So if I talk an injective function and countable, is the first half or the second half? Or it really is a silly question? You know, in math, essentially is the definition. So, short answer. I don't think I can say that the midterm in the second half, and you can forget the first half. Right? When we talk about probability, we talk about sets. When we talk about combinatorials, we make the distinction between a sequence, this is a permutation, or a set, this is a combination. So, I think the right answer is that we include everything, because you cannot forget the first half when you are doing the second half. Did I answer your question?
Yeah, but I wonder if you're still going to ask us to do proposition logic.
So, according to the schedule is included. All right? So the only thing that we cover that is out is trees, because we haven't done the homework yet. We haven't finished that section. And I'm planning to finish it today. Oh, you are not seeing it. Why? So something happened. All right. So my plan for today was, or is, to review the material on the trees that we did last week, to finish that section, and to spend time on the material for the second midterm. So I'd be happy to take the questions, to do examples, exercises, anything you want. So next week we start fresh on the final section, and I think everything will be fine and will be on track. Does it sound good? Is there anything we should address before, just for planning? Yes?
Are we going to clean the calculator, not to make sure for the common parts and calculating stuff?
No. I think all the problems are such that you should be able to do it in seconds. So the biggest multiplication will be 2 digits by 2 digits. Good question. Anything else? Yes?
Homework 5 is over number 9.
Number 9. Oh, this is homework 5. Homework 5, problem 9. All right. This was just to do something which is a little bit different. So first, you have to understand the problem. So, suppose you have a merry-go-round, and the merry-go-round is round, and there are people here. I'll call them A, B, C, D. So here you can have A, B, C, and so on. And now, look at this spinning. And so you are outside the merry-go-round, and you see the people keep going. When do you say that the two arrangements on the merry-go-round are different? I'm sorry, I cannot hear you.
When people are in different positions.
Yes. So what does it mean in different positions? So the problem is that one, that you cannot say who is first, right? Because they keep moving. If you look a second later, someone else is first. So what does it mean to be different? That at some point in one arrangement you have A followed by B, but in another arrangement you have A followed by C, right? All right. So is this answer enough to try to solve it or not? Because maybe this was the hint that you needed. Yeah? All right. So what would be the answer? How many people we have here? 4. So let's do a merry-go-round with 4 people. A, B, C, and D. Right? So now as it spins, it becomes A, B, C, and D. Is this the same or not? Is the same, right? So basically the first one that we put there, it really doesn't matter, because every second or fraction of the second change. So the choices are how many I can put second, how many I can put third, and how many I can put fourth, which of course is 1 because it's the last one. And so once you pick the first, in how many ways you can pick the second? 3. In how many ways you can pick the third? 2. So what's the answer? 6. Good question. I mean, this is not trivial. First, you have to figure out the problem. And then answering is simple. Yes?
So if we have the same sort of problem,
I'm sorry.
if we have the same sort of problem, we have like 4 students and like 6 spaces.
4 students and 6 spaces.
Yeah, so there's like one space essentially, and kind of treat it like that.
So you have a bench, like here, there are 1, 2, 3, 4, 5, 6. Okay, you want to know in how many ways?
Merry-go-round style. So like,
Oh, merry-go-round style.
yeah. Isn't it just the same like permutation thing, and then you just divide it by 6? Because you divide by the number of spaces when you have repetitions?
Yeah, I think so. I mean, you divide by 6, it means that it doesn't matter really who is starting.
Yeah, as long as the order
Right.
essentially the same.
Yes. Yes?
We worked out homework number 6,
Problem
problem number 9.
number 9. So we did the problem number 9. Did I miss something?
Number 6.
Oh, homework 6. So homework 6. Oh, this was assigned today. Yes. All right. Thank you. All right, so again, let's try to understand the problem first. So here says 40 students out of 100 like biking, and 50 out of the 100 like walking. All right? So first, let's try to represent this. So because we have out of 100, suppose that you have 100 students, right? These are 100 students. And we say that 40, which is a little less than half, which is this one, I hope looks a little less than half, 40 likes what? Biking. So this is biking. And says 50 likes walking. So now we could have 50 that include all those 40, right? If I take this side, or if I take the other side, the 50, they don't include any of those 40. And we don't know this. But we know what? All right, so of these that like a biking, 20%, how much is 20% of 40? 8. 8 like what? Hiking. These like hiking. And then these are 8. And then how many others there are that like hiking? 42 like hiking. Yeah? Yes? Do you see now how is the situation? We have all the information. And so now what's the question? What is the probability that a student who likes walking also likes biking? So, someone that likes walking, sorry, I said hiking but was walking, right? All right. Walk and walk. So here ask, what is the probability that a student that likes biking, what is the probability that a student that likes walking also likes biking? So how many we have that likes walking? 50. How many also likes biking? 8. So what is the probability? 8 out of 50. Yeah? Which is 16%. You are welcome. Go back to trees. Multiplicative rules. Maybe. All right. So first, what is a tree? A tree is this. Oops, you are not seeing it. A tree is a discrete structure, very, very popular in computer science. We use it for organizing information, and we gave 2 different kinds of trees. You probably are going to learn many more, or actually maybe you have 3 kinds of trees. You are going to learn many more. And we gave an inductive definition, because the inductive definition is good for computing. And so we say a tree is a pair. There are 2 things to say what is a tree. You have to tell me what is the root, and you have to tell me what are the children. The root is a value in some set. If you make a tree of integers, it will be an integer. If you make a tree of strings, it will be a string. If you make a tree of students, it will be a student. The decoration. The other one is a sequence of trees. And so it's recursive, because in order to say what is a tree, I say one of the 2 pieces is a sequence of trees. How do I get away with this? If I want a final tree, at some point these sequences of trees will be empty. There will be no trees. And so you see the example here, A is the decoration, this is a tree of letters, I guess. This is the sequence of trees. Each one is the entire tree. When I get here, the sequence of children of subtrees is empty. There are no. This one also, and in this way I finish the tree. Alright? And so, if you have to compute on this one, like finding how many letters there are in this tree, how do you do it? Well, you have 1, which is the root, plus the number of letters in any of these subtrees. And so, to find the number of letters in a tree, you find the number of letters in each subtree, plus 1 for the root. When you get at the bottom, this is very easy, because here you just have 1. And so, the number of letters in this tree is 1 plus 1 plus 1, 3. The number of letters in these trees will be these 3 that we just counted, 1, 1, and 1, and so here you have 6. And in this way you compute for the entire tree. Depending on your favorite language, you can write a program that does this relatively easily. The other kind of tree that we did is a binary tree. So here the definition is quite different. In this tree, always I have the root. Because I have a pair, and the first one is the root. In this tree, I may not have any node, because I say this tree is either of two things. It's either empty, nil, null, 0, empty tree, or is a triple. There are 3 slots, 1 is the root, and the other 2 are binary tree that we call a left and a right child. Yes?
But the left and the right child can also be null.
Yes, and eventually they will be. When we are here, this one has 2 children. This one on the left is null, and this one on the right is not null.
I just mean like, so if it's just 1, and all you have is just your root, so you have a binary tree of 1, it's still a triple. It's just that the left and the right are null from the get-go.
Right. And you can have a binary tree which is null. There, if you count how many nodes or how many letters there are, we come up 0. In many languages, probably the languages you are more familiar with, this will be a pointer, which will be a null pointer, which is a 0. In C or in C++, this is 0, so it's not even wrong to say that a binary tree can be either 0 or is a triple, which is a struct, where you have what? A decoration and 2 pointers to the children. Alright? We saw, without insisting too much, that you go from a tree to a binary tree. And actually you can do more. You can go from a forest of trees to a binary tree. And you go from a binary tree to a forest of trees. Then we discussed what is a binary search tree. A binary search tree is a binary tree, we just said what it is, with an additional condition or property. The root is greater than all the decoration in the left and is smaller than all the decoration in the right. And so you see an example there. 5 is greater than all the values that you have in the left child and is smaller than all the values that you have in the right child. And this is true at every level. So if you go to 9, 9 is greater than all the one in the left, which are 6, 7, 8. And is smaller than all the one in the right, which is just a 10. So far so good? Alright, we saw that this is a structure that we use to search things inside. Why is convenient for search? Yes? Yes. So, saying talking with my hand, if the tree is balanced, more or less, is balanced. If you search a value, you look in the root, if it is not that one, what do you know? That you can toss away half of the value that you have in the tree. Tossing half is very, very powerful. If you have 1 billion values, you do this 30 times. 30 times is an incredibly small number for a computer. You do it in a millisecond. And so you find the value out of 1 billion. Seems a needle in a haystack, and immediately you get it there. So this is why we study this structure. A binary search tree may not be balanced. You may be so unlucky that you always go down all left or all right, so it becomes like a list, and you have to look all of them. This is a disaster. So you will learn some trees that as you build them, they remain balanced. If you keep going down one, at some point things get to move around, it's complicated, and then get the balance. Alright, so we studied how to search, insert, and delete. Search and insert is relatively simple. You look at the root. Based on that one, either you do or you answer, or you go down left or you go down right. Deleting is a little bit more complicated, and we distinguish various cases. If what you delete is a leaf, get rid of it. If what you delete has only one child, pull up the child in the place where you are deleting. You pull up the child and everything attached to the child. If there are 2 children, you have to pick the leftmost of the right child or the rightmost of the left child. Why? Because these 2 are the closest value to the one you are taking out. Alright? Alright, so we saw an application of this one to decision trees. You may remember the puzzle that we solved with the coin, that one was lighter. There are many variations of this. If you go on the internet, you find some which are fairly complicated. Like you have 12 coins and you don't know whether it is lighter or heavier, and yet you do it relatively quickly. And we saw another application, Huggman codes. This is used to compress information, and we had that algorithm. Basically, the algorithm starts by having a tree for each letter and merging the 2 trees with the lowest probability. And after you do this one, you still have a bunch of trees. You merge the 2 with the lowest probability, and you merge. And every time you merge, you label one side with 0 and the other one with 1. And to find the encoding, you traverse from the root to a character which is at the bottom, and the traversal will tell you the bits for that character. Far so good? Alright, so now we do traversal. First, let's try to understand what a traversal of a tree is. If you have a tree, we'll do this with binary trees. A traversal is the sequence of all the values, all the decorations that you have in the tree. Each decoration occurs in the traversal and occurs only once. So, for example, if I go up and I see this tree, a traversal will be all the values that are in the tree. So it will be a sequence where I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Maybe not necessarily in this order. And so there are 3 traversals. One that says, if you have to traverse a tree, and the tree, this tree is empty, null, 0, the traversal is the empty list. There are no nodes there, so the list is empty. Otherwise, we care when we visit the root. We have this triple. Now I'm going to write the algorithm. We care when we have this triple, we care where we put the root. So we look at this triple and we can make three decisions. The first one, we put the root first and then we take care of the children. Or we take care of the children and we put the root last. And finally, we take care of the left, we put the root, and we can take care of the right. So informally, you write the algorithm in this way. So, yes, so we call this pre-order when we put the root first, in order when we put the root in the middle, post order when we put the root at the end. And so, let's just try to do the pre-order. We said that the tree is either the special value null or is a triple. So I'll write it in this way. Pre-order of null is what? The empty list. I write the empty list in this way. Pre-order of what? I have a left child, a decoration, and a right child. And so what do I do here? Pre-order says put the root first, so I will put D, followed by what? Pre-order of L, followed by what? This followed by what I will write with a plus plus for concatenation, plus plus pre-order of right. If instead of writing them I do something else, typically in a book you will find a visit D. You do on D whatever D expects. Should we run this by hand on the example? So let's run this on this one. So when I call this algorithm on this one, what do I have? I will call pre-order of what? Thank you. The tree on the left, 5 the tree on the right. This is L and this is right. You with me? So we will output the 5, then we will call pre-order on L. What is L here? This will be the left of 2, 2 and the right of 2. You with me? Pre-order of what? Here I will have the left of 9, 9 and the right of 9. You with me? And so now, should we try to do this one? What will be this one? 2, right? Followed by what? Pre-order of the triple, the left of 1, 1 and the right of 1. You with me? Plus plus what? Who wants to tell me what is here? Pre-order of the left of 3, 3 and the right of 3. Yes? And so what is pre-order of 1? Will be 1 plus plus what? Pre-order of this null, because this 3 is null. Plus plus pre-order of null. You with me? And so this one will be nothing. No. This will be nothing. So at this point I have this 5, 2, 1, followed by what? This one is here, because I'm doing the pre-order of 1. The pre-order of the 3 root at 3, and the pre-order of the 3 root at 9. So now I speed it up a little. What is the pre-order of the 3 root at 3? 3. Nothing is coming from the left child. What is coming from the right? 4. At this point, I've done all this one here. I've done all this one here. Should we do quickly the one of 9? What I will have there? 9. What the left child is going to give me? 7. And then 6. And then 8. And then the right one is 10. So this will be the pre-order of the traversal of these 3 that I have here. So now the post order and the in order are very simple. To do in order, first we do the left, then we put the decoration, and then we do the right. And to do the post order, we do the left, we do the right, and then we put the decoration. Which one do you want to do first? Post order. All right. So you lead the show. We do post order of this one. What is the first sub-problem that you solve? Do the post order of the left. Right? So forget everything else. Now we do the post order of the left. So, what is the post order of the left? What is the first problem you have to, sub-problem of this one you have to do? Do the post order of the left, which is just 1. Good. Then we do the post order of the right, which is 3, 4. So what is the first sub-problem we solve there? Right. 4, and then 3. And so as we start, we will get what? 1, 4, 3, and 2. Yeah? We do post order. So now we have done this one. The root is still to come, because post order means that you do this last. So now we do the post order of the right child of the root, which is the one at 9. So what do we do first? Go to the left. Fantastic. So now we have to do the post order of 7, 6, and 8. What do we do there first? 6. So here is 6. Then what do we do? To the right, 8. And then what do we do? 7. Fabulous. And so now what do we have to do? Do the right of 9, so it's 10. And then 9. And so this is the, oh, you didn't see it, I wrote it exactly as you said. And so this is the pre-order, this is the post.
And 5.
Say it again?
5 after 9.
Yes, thank you. I forgot. You need a stack in your brain for not forgetting where you are in all this. Yes?
Should we not write like empty brackets for no children?
No. What we want is a sequence. So, this is not really a good sequence. Maybe I should put the commas between them, some brackets, but I write them in the way I compute. Yes. So these pre-order and post-order, we did it for this binary tree, but you can do it for any tree, right? So if we go back and we look at this one, we can start producing this. If I have this tree here, which is not a binary tree, and I say I do a pre-order, what will I write here? A, and then I do all the children, So I start to do the pre-order of the 3 rooted at B, then the pre-order of the 3 at C, then the pre-order at D, then the pre-order at E, and so on. Pre-order and post-order goes for any tree. In order, only for binary. Why only for binary? Because in a case like this one, where do you put A? After B, after C, after D? You don't really know. If you have 2, it's very easy. You put it in the middle of the 2. But if you have more than 2 or less than 2, you wouldn't know where to put it. Alright? So finally, I want to do the in order of this one. In. And so let's say one more time how is in. In, you do the left, then you put the root, and then you do the right. So if I do the left in order, what's going to happen? I do the left again. So the first one that I put there is 1. You with me? Then what do we put there? The root. And then we do the right chart. So this is the 3 rooted at 3. What do we do there? Left, there is nothing. 3 itself, and 4. Now we have done all this, we put there 5. Yeah? And so now we have to do the right, which is the one rooted at 9. What do we do? Left. Is the one at 7, what do we do? Left. So here we get the 6, then we get the 7, then we get the 8. Now we come back. There is 9. We put it there, and then we put the 10. So if you look at this one, surprise, surprise, it's sorted. Now, it's not a surprise that it's sorted. Who can tell me in one sentence why it's not a surprise? Yes?
Because of the way that tree works, so the root is in between.
Right.
On the left.
The tree is bigger than all the one on the right and is smaller than the one on the left, so really goes there in the right place. And the same happens for the subroot. So this one suggests a way to sort, right? If you have to sort, insert all the things in a binary search tree and then print it in order. Yeah? All right. Tim, are you happy? Good. All right, so let's move on. All right, we represent expressions as binary trees. So let me write an expression here. What do I mean by expression? By expression, I mean things that we evaluate. So here I have addition, multiplication, subtraction. I can put other things like a power, a logarithm, a sine, cosine. We make this expression, and then we want to evaluate it. So suppose that I write this expression, 1 plus 1 times 2, and I want to evaluate it. So first I have to represent this as a tree. So how do I represent this as a tree? An expression is either of two things. Again, here you have a inductive recursive definition. An expression is either a number or an operation. Here I consider only addition, multiplication, subtraction. Is an operation applied to two expressions. So here, this expression 2 is just a number. The entire expression is this operation applied to two expressions. One is 2 and the other one is 1 plus 1. And so how do I represent this one? Yes?
If you're doing it in order, you go star as the root. The left child would be plus. The left child and the left child would be 1.
Yes.
The right child would also be 1.
Yes. Eventually we will traverse it. Yes. You're right. You are just a couple of steps ahead of me. And so, how do I represent this as a tree? If it is an operation, the operation is the root. And then the two children are expressions. Right? This is the definition. An expression is either a number or is an operation applied to two expressions. And so, I put this one. This side I have 2. This is 2 is an expression when I put it there. What do I have on the right child? I have an expression that comes from 1 plus 1. How do I make this one? Because it's an operation. This is the root. Here I have 1 plus 1. So far so good? Alright, so when you have an interpreter, do you know any interpreter? Python, for example, we call it is used an interpreter to evaluate your things. Of course, you can optimize. Represent this expression inside the machine as a tree. How is this done? Well, you have two kinds of nodes. One that contains a value, and the other one, which is a triple, where you have the operation and the two children. All right? So, how do we evaluate this? Eval. And here I have two cases, right? Number or eval, and here I have the expression left, operation, and right. So what is the evaluation of a number? The number itself. Fantastic. What is the evaluation of this one? Fantastic. So this will be the evaluation of the left with the operation, whatever it is, of the evaluation of the right. You see, this is recursive, of course. And so, let's apply this to this very simple example. So, when we call the evaluation of that expression, which case we are in? The second, because it's not a number, right? So what do? We evaluated the left. What is the value of the left? Will be 2, right? We are looking forward. What is the evaluation of the right? 2. What is the operation? Times. So the value of that one will be 2 times 2, which is 4. In doing this one, we have to evaluate the left, which is an addition, right? So which case is the addition? The second. We evaluated the left, which is a number as value 1. We evaluated the right, which is a number as value 1. And then we do the addition. You with me? And so, in the Python interpreter, you have a function eval that you feed the expression that you have to evaluate. And really, we do this. Now, this is not the best way to evaluate it. Why? Because for once, you have to write these recursive things. And so every time you make a call to that, you have to create a stack frame if you know what it is, where you have the return address and all these kind of things. Not convenient. So a compiler, try to do all this before you run the program. And does it in something which is called Polish notation, Some cases you can call this a stack machine. Polish notation, because this was invented by a Polish guy, which has one of those names where there are 20 letters and one vowel, all the other ones are consonants, so you have no idea how to pronounce it. And so it was complicated, and so they call it Polish rather than the poor guy made. All right, and so how you do it? You can do a traversal either pre or post. So here I will start doing a post-order traversal of that one. So let's do a post-order traversal of this one. As an exercise, you should do it on your piece of paper, and then I'll write it here. So, should I do it, or you want to ask or say something?
I have a question.
Yes.
In something like this, where you're actually storing two different types of data types, here you're storing operations and data, physical data, like one.
Yeah.
Doesn't that cause you to note that your tree actually contains two kinds of data?
So, typically, if you do it in an object-oriented programming like C or Python, you will have a class expression, which probably is an abstract class or an interface, and then you have subclasses, one of which will be addition, one will be multiplication, and you never store the operator there.
Okay.
The class itself knows.
That makes sense.
So when you call eval, this class knows, this object knows that is an addition, will evaluate the two children and do the addition because it knows I am an addition. You are a multiplication, you will do the other.
How do you note that in a more formal setting like with this, if we're doing like a formal tree notation of this set? How do we tell these people that we're writing to, like say for the paper, that we're going to have operations be stored and numbers, or do we just write that?
So if you really want to do the operation and be generic, we can even hack the code if we have time and we do it. You represented this with the token.
Oh, okay. So symbolically you say this.
Right, and then you have a case statement that says if the token is addition, do this. If the token is multiplication, do that.
Okay.
Of course, you can use a pointer to a function,
Yeah.
and you can be as fancy as you want, but we don't have to. All right. So I was doing here the post-order traversal, right? So if I do a post-order traversal of this one, what do I get? Sorry, yes, you are seeing it. It's 1, 1 plus 2 star. Yes? You with me? And so this can be compiled on standard architecture like push one on the stack, which probably is a single machine instruction to do this. Push again one on the stack, and then on the stack machine you have an operation that says take the two elements which are on top of the stack and add them together. And then you push 2 on the stack and you multiply them. Here I have a calculator of this kind. Let me write it, let me bring it up so we can see it. So here when, oh yes, when, let me make it a little bit bigger. When I type a number, the number goes on the stack. I don't have to say anything else. So here if I type 1, oops, you see nothing happened, but now 1 is on the stack. I think that the command to look at the stack is F. Right. F is telling me this is your stack. Now I type a 1 again. Now I type F, and now I have 2 1 on the stack. You see it? Now I type a plus, and this tells the machine, pick the 2 things that you have on the stack. Take them out, do this operation, and put the result back on the stack. So if I type F now, what do you expect to see? Here you have it. Now I type 2. What do I have on the stack? Now I do multiplication. What do I have on the stack? 4. So here I could do 1, 2, 3, 2, 3, 4. If I type an F, what do you see on the stack? 1, 2, 3, 4. Now I can say star, star, star. What do you expect to see on the stack? All right? All right. So, here we saw what? We saw first, if you have an expression, how you represent it as a tree. The numbers are the leaves, the operation are the branches. How do you do it? You take the last operation that you have to do, you put it in the root, and you evaluate the 2 children. All right? Then we saw that if we change this, if we traverse it in post order, we get the information that we need to generate code for a compiler. This way to evaluate is much, much more efficient. You really go down to machine code, and the current architecture developed in the last 30 or 40 years exactly to do efficiently these kind of things in a few hours. Yes?
So this kind of notation, there's no precedence, right?
Right, you lost everything. In both cases there is no precedence and associativity anymore. So let's make another example which is a little bit more difficult. Suppose that I have 2 plus 3 times 4 plus 5. Here I want the tree representation of this one, and I want the reverse Polish notation for this one. So the first thing you have to do is to put the parentheses. You know where they are, the parentheses, but there we don't see it, which is not very convenient. So where are the parentheses there? Right, so 3 times 4. Let me put this here. And then where are the parentheses? You, with this color, you can hardly see it, right? And then where are the parentheses? 2 plus and everything else. So why first the parenthesis 3 times 4? Right, because multiplication has higher precedence than addition. All right? We know this from grade school. Then why the other parenthesis is 2 with the plus 3, 4? So this is called associativity. And the associativity is left to right. So if you have A plus B plus C, you start with AB and then you add C. Alright? So now that we have this one, we put in the root of the operation that we do last. Or if you want, you start to build this from the bottom with the operation that we do first. So I start with the last. Which is the last that we do? Right, this plus here, so I will put this plus here, and one side I know everything already because this is a very simple expression. On the other side, I have to recursively build the tree of this expression. So again, I start from the operation that I do last. Which is the operation that you do last? Is the plus. So here I will have a plus. And then on one side, I don't have any problem because there is a 2. On the other side, is simple enough. I will have a times 3, 4. Yes?
Would it be okay to switch the multiplication symbol into 2 so that since you're doing the 3 times 4 first, that would go on the left and the 2 would go on the right?
In this case, yes, but if it is a subtraction, you cannot do it. Right? All right, so now, for interpreting, this is all we need. To compute this one, what we do, we evaluate the left, and we evaluate the right, and we do the addition. Assuming that the recursion is correct, when we evaluate this one, we get a 14. When we evaluate this one, we get a 5. We do the addition, and the result is 19. All right? Now, if we have to compile this one, we do the post-order traversal. So, do it on your piece of paper. Did you get the same result? Should we test it with my program here? So here I have 2, 3, 4. Then I do the multiplication. Then I do the addition. Then I push a 5 and I do the other addition. And I print the result. You with me? 19. Isn't it beautiful? All right, the typical Polish notation is a pre-order traversal. But typically when you have a stack machine, what you really want is the post-order. So this is called reverse Polish notation. In the 80s, Hewlett-Packard came up with one of the first pocket calculators, which was meant for engineers typically, and was a reverse Polish notation. You would use it exactly as I use this one. And then a few years later, Texas Instruments did something where they had the registers. And so now you don't have to know the reverse Polish notation and all this. You compute something, then you have to put it aside for a second. You say, put it in a register tree. Then you do something else, and then you say, pick what I put before in register tree. And on one hand, this is simple. On the other one, if you have 3 or 4 registers, you have to remember which you put in which register in your head. So, wasn't that easy? Here, you don't need any register. If you need the temporary things, you just leave them on the stack, and later on, you pick them up. Yes?
For order sensitive operations like division,
Yeah?
so if you've got like 2 numbers on the stack, which one does it use for which position? Is that undercounter?
I think the second is in the top, because you start like we do here. All right, sorry, we got carried away. Let's take our 10 minutes and then we continue.